We'll move on to the irreversible Carnot engine. So the irreversible, sorry. Okay, it's not much different, except that that's our Carnot engine. Okay, that's the Carnot cycle. The first one is an isotherm. I make it irreversible. So what I have is then to start from here, I'll end up over there. Right? I can't plot the isotherm, but the starting and final points are the same. Now, I don't have to bother much, but I already know that the work done reversibly is much more than the work that will be extracted from the system irreversibly. So what I can write is that the work done reversibly by the system, so which means minus of that, because when the system does work, it's negative, is greater than minus of work done irreversibly, right? And since it's a cycle, delta U must be 0. So I know that delta U is equal to Q plus W. Reversible is equal to Q plus W irreversible, and I already know that minus W reversible is greater than minus W irreversible, which just means that the heat that is required, I don't know why this is making sense, the heat that is required reversibly is less than the heat that is required irreversibly, right? No, sorry. The heat that is required irreversibly is less than the heat that is required reversibly. Of course, I mean the efficiency of the reversible engine is the maximum, right? So the heat required for the reversible engine has to be less. Right? Okay. Let's not bother about what it is. Let's put it over there. Q reversible plus W reversible is equal to Q irreversible plus W irreversible, right? And I take this on the other side, Q reversible minus W irreversible is equal to Q irreversible minus W reversible. Now I know that minus W reversible is larger than minus W irreversible, so Q reversible has to be larger than Q irreversible. Why? So delta U is equal to Q plus W. Now then only I have got it. Right? Okay. See, all that I am saying is that delta U is equal, either in the reversible case or irreversible case. Yes. So if this term is small than this term, then this term has to be larger than this term. Right? Which sign? Yeah, the sign convention holds true. So if I do work, if the system does work, it's negative work. Right? So depending on this one, so the first one, the system does work. That would be negative. So this is the total one, right? This is Q for this plus W for this plus W for this plus Q plus W for this plus W for this. For the adiabatic, the Q is 0. Yeah, this is for the entire cycle. I mean, I could even take it for just this one because the rest of it is the same. I could only take it for the first isotherm because the rest, everything is same. Baki to I have assumed that the rest of the thing is all reversible. Only I am considering the first isotherm to be irreversible. And that makes the entire cycle irreversible, right? Even if one step is irreversible.
The efficiency of reversible engine has to be maximum. And Q reversible should be less than Q irreversible.
Well, if the works are same, right? So yeah, so the efficiency then comes out to be of the reversible case. So the efficiency was 1 plus Q2 by Q1, right? And Q2 is the heat that we've exchanged in the third step, right? So that's always reversible. It's Q1 that is going to make all the difference. One plus Q2 reversible by Q1 irreversible. Right? And now, in fact, I could answer your question even with this definition. This is Q1 irreversible, right? And this is the heat that is being pumped into the system. This is Q2 reversible, which is being taken out of the system. So this is a negative sign. This entire thing has a negative sign, right? And if I write the efficiency of the reversible one, then that's 1 plus Q2 reversible by Q1 reversible. This is also a negative quantity, right? Since Q1 reversible is large, yes, since Q1 reversible is large, this is a small quantity. So 1 minus a smaller quantity, 1 minus a larger quantity. So this efficiency of the irreversible one would be less than the efficiency of the reversible Carnot cycle. Since the heat exchanged in the case of reversible is larger, also the heat that will be exchanged in small steps would also be larger. Right? DQ reversible would be larger. Right? If I make equal steps. So what I can also write is that dq reversible by t is larger than dq irreversible by t. Temperature is constant, that's right. One. It need not be constant because this is the small change in temperature. Right? For this particular case, of course, we use the isothermal expansion as the example, so the temperature is constant. But in general, it need not be. It's actually written more like this: dq irreversible by t is less than, is the same thing, dq reversible by t, because this is this is more common form of writing it, because we already know that dq reversible by t is the state function entropy, and the cyclic integral of a state function is 0. So what it gives me is the most celebrated statement that the cyclic integral of dq irreversible by t, that is the heat exchanged irreversibly divided by the temperature at which it's exchanged, is less than 0. Or in general, I can write integral of dq by t is less than equal to 0. Okay. This is known as the Clausius inequality. Okay. So this is something that I had told you on the first day when we started with the second law, and that's a kind of proof for that. This is the basis of the second law, that the entropy of an isolated system always increases. The entropy of the universe always increases, right? Universe is an isolated system, and we'll come to that. It's a very strange thing. You would be imagining, when the cyclic integral of ds is less than 0, how does it always increase? This is a cyclic integral. Okay. That is a spontaneous process. And let's see how we can actually work for that. For a? The total entropy. For a system, you can imagine that if I think of crystallization, things are getting more ordered for the system. So the entropy of the system is definitely decreasing. Why crystallization? If I say a gas condenses, given a simpler example. So in all these cases, the entropy of the system is decreasing. It's the surroundings that matter. It's the total system of any isolated system.
So हमने पूरा सिस्टम का सराउंडिंग तो लिए नहीं, हमने तो सिस्टम का ही लिया है.
नहीं, पूरा है.
वो तो सर dq will be of system.
नहीं, it's the heat exchanged.
Sir, it will have a sign now. And the sign will be of system. If dq is positive, then it is for system.
Yes.
With sign, sir, it's taking system.
This is the heat exchanged, right? Heat exchange between the system and the surrounding. See, when you're talking of system or surrounding, then you have to worry about the state functions. Okay. So let's worry about how we come to the second law that you are more familiar with, starting from the Clausius inequality. And that is, let's say we start with point 1 and we go to a point 2. Okay. And if you remember that Clausius statement that all spontaneous processes are irreversible, right? So I do it spontaneously. So this is irreversible. And since I want to calculate for the entropy of the complete universe, so I assume that this is an isolated system, right? So no heat is exchanged between the surroundings, no mass is exchanged between the surroundings, right? So this system is system plus surroundings. It's isolated, right? It's as good as the complete universe. Isolated. Unfortunately, I do not know what the path is. But entropy does not depend on the path. So, in order to calculate entropy, what I do is to bring back the system from point 2 to point 1 through a reversible path. If I do that, I can calculate the entropy. And since entropy is a state function, it does not matter. Right? So let's do that. Let's then take a reversible path, construct that. So this is our reversible path. And that is what I wish to use in order to calculate entropy. And since I am going to make a reversible path over there, since I am going to make this reversible path over there, I have to do some extra efforts. The system cannot be isolated anymore. So I might have to supply some heat, take some heat, do some work, whatever. But the system cannot be isolated. So this is not isolated in the second part.
So we change the system.
The system is the same. The system is absolutely the same. The starting point and the end point. They are exactly the same. So the system could be, for example, going from volume V to volume 2V. Right? So all I am doing is bring it at pressure and temperature. Define pressure and temperature. All I am going to do it is from VPT, it has gone to 2VPT. Now I am going to bring it back from 2VPT back to VPT. Right? For example. But I am going to bring it back through a reversible path. And then let's calculate what exactly are the quantities we can get. So first is the irreversible path. The heat exchange is 0. It's an isolated system. Yeah, just by the fact that it's isolated, Q irreversible is equal to 0. Right? If Q irreversible is 0, then dQ irreversible by T is also naturally 0. There is no exchange of heat. Right? So if I use the Clausius inequality now, which is given over here, dQ by T is less than equal to 0. If I use this, then I have to consider for the two paths, the irreversible plus the reversible path. That means what I have to see is dQ irreversible by T integral from 1 to 2 plus integral from 2 to 1 dQ reversible by T is less than equal to 0. This is what the Clausius inequality is stating. and I already know that this fellow out here is 0, because the heat exchanged irreversibly is 0. It's an isolated system. And this fellow, the second one, the second term we recognize, that's the definition of ds. So that's integral from 2 to 1 ds is less than or equal to 0, right? So ds, which means delta s on going from 2 to 1 is less than equal to 0. The delta s on going from 1 to 2 would be exactly the opposite, because in a cyclic process delta s has to be 0. So delta s for a process then is necessarily greater than equal to 0. Right? Yes. This is the total, right? If I go from point 1 to point 2 in an isolated system, that's my delta S. So that means this is the total delta S. Yes? Universe is an isolated system, and I am doing it for an isolated system. I'll come. Did they tell you the truth today? But I'll come. Today you were there. Okay. So that's the statement that everybody knows. We know that if delta S is greater than 0, it's a spontaneous process, right? That's what this is saying. When it's irreversible going from 1 to 2, then delta S is greater than 0. Yes? Equal to is in the case of a reversible system. So that's a spontaneous, and each spontaneous process is always irreversible. Delta S equals 0 is reversible, something which is in equilibrium. Delta S less than 0 is impossible. We don't have a situation. Something is never possible if the total delta S of an isolated system is less than 0. If it's not an isolated system, yes, it can be less than 0. Gases do condense. Okay? So please always remember isolated system. That's very important. That is the total. What I said was that delta S going from 2 to 1 is less than equal to 0. That was up to that point, it's fine. Yes? But what we are interested is in the delta S of the process. That is from 1 to 2. And in a cycle, delta S has to be 0. It's a state function. So 1 to 2 would be minus of 2 to 1. So minus of delta S 2 to 1 would be greater than 0. Others can just please keep quiet. How does it contradict? Which one? Yes. No. Very careful about that. It's dq reversible by t. Okay. And if it is dq reversible by t cyclic, it's always equal to 0. Okay. No. So this is from 2 to 1. I want from 1 to 2. So if 2 to 1 is less than 0, then 1 to 2 is negative of 2 to 1. Negative of this quantity would be greater than 0. Right?
So here we have used directly that delta S as a state, entropy is a state function.
Yes.
So how do we exactly prove that?
You don't prove. You don't prove U is a state function. You don't prove. Okay. These are things, I mean, it depends here. Does it depend on the path or not? And then I should come back to her question that why do I need to define a quantity such as dq reversible by t? Okay. So essentially, there are two forms which we have seen how we can exchange energy between the system and the surroundings. One of them is heat and the other is work. Now, work when I do, I mean I'm trying to push something. So, all the molecules, if I look at the molecular picture, would be pushed in a particular direction. Right? It's not a random thing. It's more of a directed energy. So, all the energy would be going in one particular direction. But if I heat up the system, then it's more of a random motion. All these molecules could fly in any direction. Heat is not directed. Right? So, in certain sense, heat is a measurement of randomness. The more I heat the system, the more random I make it. Yes? But then heat is an extensive variable. Right? I want an intensive variable for that. One thing. And I want a state function. So, how to make it intensive? Normally, if I have volume, how do I make volume intensive? I divide it by the number of moles or by the mass of the sample, right? Per unit mass. Now, heat is being exchanged at a particular temperature. Yes? So, I intensifies it by dividing it by the temperature. You know, what difference would it make? If I am at a very high temperature and I supply 1 kilocalorie of heat, doesn't make a difference. Right? It does not tell you exactly how much randomness I have generated. But at that temperature, if I divide that value by the temperature, then I know exactly what is the amount of randomness that I am generating. It's being normalized every time. Right? The amount of heat that I supply at the given temperature.
Why is it reversible?
Why is it reversible? Is because you want a state function. Right? If it was irreversible, it wouldn't have been a state function. You can, for a reversible case, you can always reverse it at any point of time.
What's the use of having it as a state reversible? What is the use of having it reversible?
So you want it to define a state function, right? So you want to associate the randomness with a given state of the system, right?
then randomness or that intensivization by dividing with that's okay, but sir, how do you do this? The heat is a function of temperature difference.
No. Heat is how much heat I supply, right?
But sir,
I mean, you know about latent heat. You know about latent heat, right? There's no change in temperature over here.
Heat will be zero at that time.
Yes.
But sir, how do you intensifize that statement I don't get? Intensivization by dividing by.
So this at a particular temperature, right? How much heat you're taking out? So if I just say I'm taking up so much amount of heat, yeah, doesn't make a difference. Okay, if I'm at 100 Kelvin and I want to raise the temperature further, and I take up some amount of heat, I'll be able to raise the temperature something. If I'm at 1000 Kelvin, I take the same amount of heat, I won't be able to raise the temperature by the same difference. Right? But if I take the same amount of Q by T, I'll be able to raise the randomness to the same level.
So,
I mean, one thing. It's not so intuitive, such as volume and number of moles. So you can never be so satisfied as in those cases.
Measure of randomness, we just say that we'll be able to get that of randomness, but how much that randomness?
Okay, for the measure of randomness, we'll come to the third lesson. When we can actually have actual values for entropy. In fact, today I'll show you some examples. Yes. So, which is, if it's irreversible, I really don't know how much heat I'll give and take between these two. But if it's a reversible path, I know exactly what is the heat that is required. Okay. So the more familiar statement is that the entropy of the universe increases. Right, that's your second law. Yeah. We could do some very quick calculations and show you some very obvious things. Yeah. But that's the starting point, so let's just show this. If I bring two metallic blocks in contact, one at a hotter temperature, one at a colder temperature, and we already know from common experience that both of them will come to the same temperature. Okay, and this is driven by entropy. So let me show you that. Let's have these two temperature blocks. So now I need an isolated system, right? See, completely isolated. And then I have two metal blocks, T1 at temperature 1 and temperature 2. Okay. So now, initially I say that okay, T1 and T2 are different. Huh? So what is the change in entropy of the two blocks? So what I need to calculate is essentially ds, which is equal to ds of block 1 plus change in block 2. It's an isolated system, so whatever heat is lost by one of the blocks will be gained by the other block, which means that dq1 by T plus dq2 by T1 T2, right, would be equal to dq1 into 1 over T1 plus 1 over T2. Oh, sorry, minus. Thanks. Minus. Right. So dq1 into T2 minus T1 over T1 T2, right? That's equal to ds. Now for a spontaneous process, ds should be necessarily greater than 0. So let's do that analysis. If Q is the heat, if dq is positive, then for this ds to be 0, sorry, greater than 0, T2 has to be greater than T1, which means that if T1 is at a lower temperature, then heat will flow from 2 to 1. This is obvious. The other way around, if I look at it, if this fellow is negative, then T1 has to be at a higher temperature and heat will flow out of system 1. Right? Fairly simple, fairly common sense, but what this example just shows you is that these kind of things, all the spontaneous processes that occur, can be described, can be explained on the basis of the changes in entropy. Let's go back to another system that we have already studied, and that's the Joule expansion. Okay, in this case, remember we had this one balloon with some gas and the other balloon had vacuum, and suddenly this throttle was open. So, and that was also an isolated system. Remember? Yes. So let's just make a small schematic over there. Isolate this entire system. Make two partitions. The first one is gas, volume V, and here we have vacuum, again volume V. Okay. So the gas, let's make it for ideal gas, then things become easier to understand. So gas is at volume V, let's say temperature T, pressure P, and the Joule expansion is an adiabatic expansion. There is no heat exchange, it's an isolated system. It's irreversible, it's against vacuum. V, temperature remains the same, because you remember delta U was 0. Pressure remains the same. Pressure is half. Right. Pressure is half. Oh, sorry, that's fine. Okay. So delta U was 0, work done was 0, Q was 0. Okay. Now let's calculate what's the change in delta S. Now I already know this is against vacuum. Thanks, man. Okay. So we already know that this is an irreversible case. Batteries, we have to call this guy. And I don't think he's around. So the rest of the class, now I have to shout. Okay. So this is a spontaneous process, irreversible one, but if we want to calculate delta S, then what we need is to find a reversible path, right? So let's compress the gas reversibly. That means slowly I bring, let's say what has happened is that I have gone to some situation like this, and now I have a piston over here, and slowly I push this piston and compress the gas reversibly, adiabatically. Won't be adiabatically. Isothermally I can do because the temperature is the same. But if I have to do it reversibly, I can't do it adiabatically, right? So let's use it isothermal compression. Okay, and you already know the expression for isothermal compression. Isothermal ideal gas, delta U is 0, right? So whatever the heat exchange is equal to negative of work done, and work done was equal to right nRT log of so yeah, minus of RT log VF by VI, right? In case of expansion. In case of compression, it's also minus RT log VF by VI. Yes? It's the same. Only thing is the volumes will be different. So the volume final is V and initial is 2V, and then the minus sign, so I just change it. 2V by V. So that would be, in fact I should not actually have done this integration, but I know that temperature is constant, so it does not matter. Yeah, otherwise actually what I should have done is dq reversible by T is equal to minus of dw reversible by T, right? And then integrated from 2V, or I can't integrate dq, but integrate it over whatever limits, integrate this from 2V to V, which would give me the same results. Okay, it doesn't matter, but going properly, that would be plus of P dV by T integral 2V to V, and P by T is nR by V, right? So nR dV by V of integrated from 2V to V, which would give me the same expression nR ln 2. Minus was there. So from V minus, right. ठीक है? So now that's what the change in entropy is, right? That is the change in entropy of the reversible thing, compression. So the expansion is negative of this, which means delta S of the spontaneous process is equal to nR ln 2. Right. For 1 mole of gas, I could just say R ln 2. For the expansion, for the spontaneous process. Make sure that this is a positive number. ln 2 is greater than 1, greater than 0. Okay. So, this brings me to another thing. What it says is that the change in entropy, if I increase the volume twofold, is nothing but R ln 2. Okay. This stands for the twofold increase in volume. Temperature is constant. We will come to the temperature part. Okay. I'll show you how entropy changes with temperature after some time. Well, you already know. I mean, in Qt 0, some of you have already solved it. Right? Anyway, now the thing is that this brings us to the molecular approach of entropy and its association with randomness. This is Boltzmann's formulation of statistical entropy. What he said was that the entropy of a system, not the change in entropy, but the entropy of a system, S is equal to K ln W, and this is the Boltzmann's constant, 1.381 into 10 to the power minus 23 joule per Kelvin. Right. So yes, there is a randomness associated with a change in volume also, right? We'll come to those things. Wait. First, let me discuss the molecular interpretation. So what it says is that this is the Boltzmann constant, right? I'm sure everybody is aware of this. R equals K times Na, and W is the number of microstates. Microstates. Okay. What it means is how many possible permutations are there to actually for the same energy, right? For the same energy to actually arrange different things. Okay. Or rather, I shouldn't say permutations, but combinations. Okay. Makes a difference because identical things when exchanged does not make a difference. In case of permutations, it does make a difference. So, for example, if I have a crystal, a perfect crystal, right, of some atom, gold atoms, right, I have only one way of arranging it for a given energy. Let's say we have only the face-centered cubic symmetry, which is possible for gold and that's the lowest possible energy. The next one is at a much higher energy. So this is the only possible way of arranging it, and I cannot change it. If I give them some energy, I'll be able to change that arrangement. But if I do not supply any energy, which is when I am at 0 Kelvin, I do not supply any energy. So I have only one possibility, which means that the number of microstates is just 1, which implies that this entropy is 0. Right? Yeah, tell me.
Can we get the absolute value?
Exactly. You get the absolute value of entropy. Right? This is the third law. But we'll come to, since we are not into statistical thermodynamics, we'll use the same classical method to come to the third law. But I'm just telling you the molecular interpretation for the timing because I have just discussed one example which brings you to this concept. Now think of a box which has collection of gaseous atoms or gaseous molecules, whatever. And so there's a volume V, right? And now I give you another volume V, which can also be filled up with these gaseous molecules. So initially I had some number of microstates W, now I have twice the number, right? So the change in entropy would be just log 2. And since we are dealing with 1 mole, then it's, see, each atom or molecule has a position somewhere in this box. There is 1 mole of atoms. So that means the number of microstates would be, let's say, C is the number of microstate for each and every molecule. Yes. So I have C to the power Na, 1 mole of molecules. So each of these have this, so I have C possible positions. Each of these Avogadro number of molecules could sit in these positions. So I have C to the power Na log of this K. So I can bring that Na over here, right? Or R log C. And just I make the volume 2 times, I make the number of microstate 2 times. W, C, whatever you want to call it, right? Whatever each molecule has, I don't know what are the possible locations it has. I mean, there could be lots and lots of them. When we go to the third law, we'll do some simple examples with defects, and you can calculate the entropies. But for the moment, you can be happy with this. Okay. Any questions on this? Good. Then we'll go and discuss some other ways of other examples where we need to calculate entropy, and to see that actually entropy is associated with disorder. Okay. So one of the cases which I've chosen, and this is a very neat experiment, I really love to see this one, is the mixing of two gases. Well, you know, if you have two containers and let's say there are these two containers over here and there's a wall separating them, and I break the wall, the two gases would definitely mix. That's spontaneous, right? That's what we understand from everyday behavior. Now, I want to see if the entropy of this mixing is positive or negative, and we wish to calculate that. So let's see the situation. The situation is, we have two boxes over here, and we have gas A on the left with Na moles occupying volume A, gas B on the right occupying volume B, and I break open the wall. Okay, this is closed, and I break it open, and the total number of moles is conserved, so there is no chemical reaction over there. The total volume is VA plus VB. So I have mixed. So the temperature is same, right? Pressure is same. Okay. These are ideal gases. Yeah, PV is equal to nRT. P of VA plus VB is equal to Na plus NB RT. That makes sense. So the pressure, temperature remain the same, but I have mixed it. Now, this is a spontaneous process, so I need to find the reversible path to calculate the entropy change that has occurred. That means I need to demix. If I need to demix, I need to find something. One piston which just pushes A, does nothing to B. Another piston which just pushes B, does nothing to A. Which means, now since people have tendency to ask me, give me a practical example. Yeah, I'm sure there must be things, or even if not, right? You know, there are all these chromatographic techniques which allow smaller molecules to pass through, for example. So some of those things could be possible, but even if they are not, let's assume that this is a Gedanken experiment. In quantum mechanics, you'll hear a lot about these. I don't know if you've already heard about the Schrodinger's cat. Those are all hot experiments, Gedanken. Okay. So what you do is then take this box and put a piston over here. Just a moment. So this piston this is permeable to gas A only, and another piston over here this fellow is permeable to gas B only. And what happens then is that both my pistons land over here, and on the left I would have gas A, on the right I would have gas B. Right. Let's start pushing them. So I'll be pushing only gas A by this piston. I'll be pushing only gas B by this piston. Right. Now this is the demixing process. Demixing. And what I wish to calculate is the entropy change for the demixing process, since this is a reversible process. Right? So I wish to calculate the entropy change, and that would be the negative of the spontaneous mixing process. Okay, so what information do I have at hand? There is ideal gas, temperature is constant, delta U is 0. Right, so let's write everything down then. Ideal gas, constant temperature, delta U is equal to 0. Q in the reversible case is equal to minus W. The reversible case is equal to, now I know what amount of work has been done. See, this fellow is permeable to A, which means this is pushing only gas B. Right? So the pressure that this piston would exert would be only on gas B. And that would cause a change in volume of gas B. So dW would be so dW would be equal to minus of P. The same on the other side. The right piston would do work on A. So PA times D volume of A प्लस नहीं माइनस ही होगा minus PB times the change in volume of B. Right? So then I need to calculate the delta S of demixing, which is nothing but integral of dq reversible by T, which is minus of dW reversible by T, which would be starting from volume V and going to volume VA in the case of gas A, PA dVA. I have gotten rid of the minus sign because dq would be minus dW, right? Plus going from V all the way to VB, PB dVB. Right? That would be work divided by temperature. Thanks. So that just gives me the same expression we worked earlier. NR NA R natural log V final by V initial. Huh? Yeah. VA by V, right? Plus NB R natural log VB by V. Right? I could define something called the mole fraction, which is XA is equal to Na by the total number of moles, XB is equal to NB by the total number of moles. Because these are ideal gases, VA by the volume of gas A divided by the total volume would also be equal to the mole fraction, because these are ideal gases. And then so this is N R XA log XA plus XB log of XB. This is delta S demixing, right? And by definition, delta S of mix would be negative of this, so that's delta S mix would be equal to minus NR XA log XA plus XB log XB. And since all the mole fractions are always necessarily less than 1, their logs would be negative numbers. I have a negative sign here. Delta S of mixing is always positive, and mixing is a spontaneous process. It's a very special case, yeah. Constant pressure, constant temperature. Ideal. Right. Okay. Then I have a cup. I have 5 minutes, so I can just finish these things. Yeah? No? Okay.